time reflection, so that when you have in a parametric oscillator, it is essential that this epsilon is dependent on time, and it gets the time is going back. I can easily explain it in a second, but it's related to the work by Matthias Fink and by Richter in Paris.
Right, you've got 4 minutes 59 seconds.
Yeah.
4 minutes 58 seconds. 4 minutes 57 seconds.
You know, it takes me completely out of my floor.
Okay, thank you. Can we sit down, please?
Very nice.
Can we sit down?
Ladies and gentlemen, we're reconvening.
So, we'll get started again. LUDWIK KOSTRO. Thank you. We have discussions outside the coffee room. So we're going to start here. LUDWIK KOSTRO is going to give us a talk on the model of the universe constructed by playing with universal constants recognized in contemporary physics. Take it away, Philip. Take it away.
In physics, we use conventional standard units of measurements. The most widely used system is the SI system. Physicists like Stoney, Planck, Kittel, and others have introduced units that are called natural units because they are determined by universal unconventional constants which govern our universe and are recognized as fundamental and important in contemporary physics. Stoney's units concern and characterize especially the electromagnetic phenomena. Planck's, the quantum phenomena. Kittel's units, the gravitational phenomena. The set of lambda units that I have proposed in some of the previous papers concern and characterize the dark energy and the phenomena connected with the expansion of the universe. In this presentation, I will introduce a toy model of some domains of the physical reality in which Einstein's cosmological constant lambda plays an important part. I call it toy model because I should play with universal constants. They are the players in the proposed game. My purpose is primarily to point at some new considerations connected with dark energy. Of course, objective problems connected with dark energy cannot be resolved simply by playing with constants. They must be addressed, first of all, by hard, sophisticated mathematical work and by precise observations and experiments. What is dark energy? Einstein made in his papers on the new ether, that now we call dark energy, a clear distinction between the physical space as such, Raumzeit als solche, or as whole, as Ganze, that is one and single. And he made the decision with this physical space-time and the infinite number of reference space-times which are geometrically composed of word lines and momentary three-dimensional spaces. The physical space-time as such, als solche, is not composed, according to Einstein, of word lines and momentary three-dimensional spaces and cannot serve as privileged reference space-time, but has a certain density of energy. Hence, according to Einstein, it should be not called vacuum, but plenum. Today we call the physical space-time dark energy, and we maintain that its energy density is constant. The The physical space-time as such is not curved by its nature and opposes itself against any curval deformation. So we can say today it opposes itself against such deformations which the lambda force and pressure. What is lambda force and pressure will be explained later. It is when physical space-time as such becomes curved because of the strong impact of great concentrations of the ponderable matter, that curved space-time becomes a gravitational field. Gravitational fields appear in the neighborhood of the concentrations of the ponderable matter. Over great distances, they disappear. When the physical space-time as such remains flat, then it is considered as inertial field. The motion of test particle cannot be detected in it. The curved parts of the physical space-time as such tends to become rectified. That's the anti-gravitational activity of dark energy. The gravitational fields are local, but dark energy is everywhere. It is well known that Einstein introduced the cosmological constant lambda in 1970 when he applied his general relativity field equation to the whole universe. Lambda was introduced into his new theory in order to avoid the gravitational collapse of the universe. Einstein was aware that he had to introduce a centrifugal repulsive pressure of the physical vacuum to regain an equilibrium in the universe. If we let P represent pressure and F force acting on a surface having a certain area, then P is given by this equation. So in order to find P, we need a force and an inverse area. Let us now see how we can introduce in general relativity a repulsive force. It is well known that in general relativity we do not speak about a gravitational attractive force. Gravitation is considered as the result of the curvature of space-time. Gravity is considered as embedded in the geometry of space-time. The deformation of space-time, however, are caused by the presence of the masses of the ponderable matter, for instance by the clusters of galaxies. However, the general relativity equation contains, in a hidden way, a force. In Einstein's general relativity field equation, there is a constant kappa, which is sometimes called Einstein's gravitational constant. The constant kappa has the dimension of an inverse force. Einstein, in order to introduce the centrifugal pressure, has chosen as the repulsive force the inverse of kappa. It means that the repulsive force is the lambda force that is given by this equation. It is great 10 to 42 newtons. Einstein and physicists did not like the name repulsive force. They prefer to say that lambda as an inverse surface is embedded in the geometry of space-time, and so it causes anti-gravitational repulsion like the curvature of space-time causes gravitational attraction. Accordingly, we can think of lambda as straightening up the space-time that becomes curved by the presence, by the impact of masses. Einstein, however, needed still a constant surface on which the lambda force acts to obtain the needed pressure. This constant is called cosmological and has the dimension of meter raised to the -2nd power. It is extremely small. Its numerical value is estimated today to be approximately 10 to -52 on a meter square. Considering the lambda force and the inverse surface, lambda itself, we see that the repulsion lambda pressure introduced by Einstein and his followers is given by this equation. Measured in human scale, it is very weak, 10 to -10 Newton per meter square. In order to obtain the whole list of lambda units, we have to use the same mathematical technology that was used by Stoney, Planck, and others. We need the 3 fundamental lambda basic units determined in our case by the 3 Einstein's constants C, kappa, and lambda. The lambda length, the lambda time, and lambda mass. Let's look for them. Since lambda is an inverse area, therefore the lambda area is given by this equation. It is extremely large, 10 to 51 meter square. The lambda, the area lambda, can be considered as an image square with a side equal to lambda length. We find that lambda length, the inverse of the square root of lambda, is 10 to 25 meter. Grosso modo 9,34 billion light years. As we can see, lambda length is extremely long, especially in comparison to the Planck length, which is extremely short, 10 to -35. As also lambda time is an extremely long time interval, 10 to 17 power seconds. That means 9,34 billion years. We still need to find the lambda mass. For many years in general relativity and relativistic cosmology, the quantity lambda mass density was used. Here's the equation. The density is 10 to -27 kilograms per cubic meter. For mass is a product of density and volume, so we can obtain the lambda mass. It is 10 to 51 kilograms. We now have the fundamental 3 lambda units, and all of them are extremely large. We can now present the whole list of lambda units, the most significant being the lambda mega quantum of energy equal to 2,46 10 to 78 giga electrovolts. And also there is a mega quantum of action. It is aesthetically very nice because it is an inverse of the 3 constants, C, kappa, and lambda. It is also very, very great. 7,23 10 to the 95 You can read. Every point in the universe from which the universe becomes visible when we connect with it a toy point observer is the center of the centrifugal pressure that is the source of the expansion of the universe in all directions. The accelerating expansion of the universe manifests itself in the observation that the universe expands at an increasing rate, meaning that the velocity at which a distant cluster of galaxies is receding from the observer is continuously increasing with time. The accelerated expansion of the universe was discovered in 1998. Cosmologists expected that the expansion should be decelerating due to the gravitational attraction of the matter in the universe. The observation proved the opposite. It is estimated that the second inflation began about 9 billion years after the Big Bang, so the expansion of the universe is thought to have been accelerating since the universe entered its dark energy dominated era roughly 5 billion years ago. This is how it was built. I must highlight a very interesting coincidence. When our universe was about 9.34 billion years old, when the lambda time became real, then the second inflation of our universe began. Our universe, because of the repulsive pressure of dark energy, began an accelerated expansion. At that time, when the real radius of our visible universe became about 9.34 billion light years long, when the lambda length became really indeed, then our universe began an accelerated expansion. At that crucial time, around this 9 billion years after the Big Bang, also the real mega quantum of action appeared and became activated, and so it began to play its part in the expansion of our universe. Perhaps it should be considered as the parameter of quantization of dark energy in the mega scale. Note that in theories of dark energy, the density of dark energy and the corresponding density of lambda mass are considered as constant. Among the constant lambda units, there are not only the above mentioned densities, but also lambda mega quantum of action and lambda mega quantum of angular momentum. Questions. They are aesthetically appealing, but do they have any physical meaning in the large-scale world? Does anything correspond to them in the large-scale physical reality? Can the mega quantum of action serve a real quantization parameter in the mega scale? Can we attribute a spin, a torsion, to the non-constant lambda energy quanta? However, we have to accept that the age of our universe, when it reached about 9 billion years after the Big Bang, we have considered it as a crucial age. At that crucial age, the quantitative relation between dark energy mass and the gravitational ponderable mass and energy was also crucial. Let us examine the relation in the standard model of the universe. The Friedman equation of the model with the curvature parameter 0 and lambda greater than 0 has the following form. It is very well known. In the standard model, the average mass density is given by this equation in the universe is considered to be equal to the so-called time-dependent critical density. It means, because in the standard model, the Hubble parameter is the inverse of the age of the universe. The average mass density is considered as the sum of the average mass density of gravitational ponderable matter and the mass density of lambda mass corresponding to dark energy. Remember that we use in the model the dimensionless density parameters, which are related by this equation. On the basis of observational WMAP 7 years result, the omega lambda, dimensionless omega lambda is 0, 7, 2, and so on, and the dimensionless omega g is expressed by this number, which means that the present day we are dealing with about 72% of dark energy and about 28% of gravitational ponderable matter. What was the proportion between the dark energy and gravitational ponderable matter at the crucial age equal to the lambda time? At the crucial age, the so-called critical density of the universe is given by this one. Then the dimensionless density parameters are here 0.33 and here 0.66. So at the crucial age of universe, there were 33% of dark energy and 66% of gravitational ponderable matter. Nevertheless, the centrifugal pressure of dark energy overcame the gravitational attraction of the ponderable matter. Why? Gravitational interactions are interactions between masses of the ponderable matter. So we can assume, approximately, that at the crucial age, the half part of the ponderable matter interacted with the second part. We can divide the matter inside the causally bounded sphere, doing symmetrical sections of the sphere into two hemispheres. Such hemispheres interact on the average at the distance equal to the radius of the sphere. Here we see this radius. At the crucial age, the Kittel's gravitational action is given by this equation where mg at the crucial moment is the half part of the ponderable matter. Simple mathematical transformation and calculation show that this constant is 8 times weaker than lambda pressure, allowing the second inflation to develop. Note that the quantity of dark energy increases when the radius r of the causal bonded sphere increases. The radius is raised to the third power according to the equation. Now let me add an interesting analogy. Note that the proposed toy model fits with the de Broglie relativistic wave mechanics that was introduced at the historical beginning of quantum mechanics. De Broglie started with the assumption, let's follow him with respect to lambda quantities. Where this is the frequency, but the frequency is once every 9,39, and you see we are reading now according to this model in the second time of lambda time. The lambda crucial wavelength was then equal to this equation, and the lambda wave period is equal to the lambda time. But are we really dealing with mega fluctuations or with mega waves in the mega scale? It sounds unrealistic. Why should we really exclude them? Have we to exclude mega waves or fluctuations in our universe? Let's admit them in our play, in the toy model. Since in each visible sphere, the distribution of the ponderable matter is dark matter, today 26%, and ordinary matter today is very random, the distribution is very random, and lambda stands in relation with the metric tensor, with its components, gamma and E. Therefore, we can try to introduce mega Heisenberg uncertainty relations concerning dark energy and ponderable matter. That is my suggestion in the toy model. However, we must be aware that at the crucial age, the lambda megaquantum of energy sent in all directions from the toy observer where the greatest, and they diminish as the age of universe increases. Perhaps the unification of relativistic cosmology with quantum mechanics can be accomplished in the large scale, in the mega domain, and not in the small scale one. In my opinion, we must first realize the unification between the gravitation that has its sources in the cosmic ponderable matter that deforms the physical space-time. This is the Einstein's theater of dark energy with constant density. Anti-gravitation, that is the reaction of the physical space-time, it is of the dark energy against the deformations caused by the ponderable matter. Masses are curving the physical space-times, and dark energy, identical with the physical space-time, is straightening up it. In the observed spheres in our universe, the observers are dealing with an interaction of ponderable gravitational matter and the anti-gravitational dark energy. The vacuum is deformed by islands of ponderable matter that is, among others, by clusters of galaxies and quasars. We are dealing with an entanglement of ponderable matter, deforming the vacuum and the dark energy, rectifying it. Gravitational and lambda interactions are entirely negligible and insignificant in the micro world of the elementary particles, but they are very significant in the mega scale among celestial bodies, galaxies, especially among the clusters of galaxies, and also inside the quasars. Therefore, the mega quantum of action, the two mega quantums of action, can play their part only in mega scale, not in a micro scale. As well, therefore, we have discovered gravitational waves when two very great black holes collide and not elementary particles. Let's consider another question. Will there be a second crucial age in the evolution of our universe when it enters in the age equal to 2 times? That is, when our universe will be 18,68 billion years old. If so, we will then have a second crucial epoch. Roger Penrose, in his book, Fashion, Fate and Fantasy in the New Physics of the Universe, shows that there are many fashions, fates and fantasies influencing the new physics of the universe. Perhaps my toy model belongs to the category of models created by human fantasy. And if Einstein were present at our conference, he would find immense pleasure in it, as in the following photo. Einstein laughs loudly over it. Thank you.
Thank you, Ludwig. Any questions?
As I understand it, recently the repulsive gravitation has been discovered and verified. Repulsive gravitation has been discovered and verified.
Yes.
So your theories started publishing into the
No, I don't quite question.
repulsive gravitation has been discovered and verified.
Who by? What? Where?
Where?
In China, in the United States, and Japan.
Well, we'll give it time. We'll give it time.
I'll give a talk.
Yeah, okay. We'll leave that for this afternoon. Anything else? No. Oh, thanks, Ludwig. We'll break. Thank you. 11:15.
Cheers. Thank you.
So,
Okay.
Martin, what is your, what does you mean that the oscillator, I mean, is it without gravity, or is flat, or is like this way, in the vertical? The oscillator in your, the very first assumption, the oscillator of light.